Minasan, konnichiwa, Zamurai Engineer desu. In this video, we will now start with the next chapter, chapter 2, which we have different topics, about 10 subtopics. First, we will talk about the first one, which is the discussion about differentiation of continuous functions. Okay. So let us proceed. So first, we'll talk about forward difference approximation. So there are several approximation method in dealing with differentiation. What is the main definition of derivative? So we have the first derivative, as in your monitor, is equal to limit of the function x plus delta x minus fx over delta x as delta x approaches 0. So for this definition, and given a finite value of delta x, so finite value of delta x, we can therefore approximate, because in practical terms, we cannot make delta x equal to 0. We can just approach 0, but we cannot in any way equal to 0. We want our goal to be as near as possible to 0, but we cannot make delta x is equal to 0. So therefore, it becomes a matter of characteristic of different engineers to approximate their problems differently by giving a certain value for delta x, which would be different from other engineers, so they can be able to estimate it better than other engineers. Now, when we are talking of the capability of the digital computers, the same matters apply, only that digital computers are very much precise and accurate because it can allow very, very small value for delta x. Okay, so in our time, when there's yet a graphical computer in our time, we have to do it, for example, manually, or to do it on digital computer, but a very rough value for delta x. But now, computers nowadays can allow very, very small value for delta x, and therefore the accuracy and precision allows greater and greater equivalent or approaching the exact value. Okay, the approximation now approaching almost 0, almost negligible error. So it is now, therefore, f prime x is approximately equal to fx plus delta x minus fx over delta x, because of finite value of delta x, which is not equal to 0 or not approaching 0 as mathematician would want to always use. But we are not mathematicians. In real world, wherein engineers are continuously solving real world problems, we are limited with physical limitation. Okay, so physical limitation, that is in manual, as I have said, when we are approximating on our time, and also the limitation of tools, the limitation of computers. We now have an easier equation, but it is only approximately equal. The good thing about this is that, as I repeat, it is an approximation, but the approximation is too near as possible to the exact value. Okay, you will notice what is the difference between the upper and lower equation. The difference is because there is no mention of limit delta x as delta x approaches 0. Okay, there is no limit. The function limits in our calculus is what? Neglected. So that mathematical procedure is neglected, and just assume that the function x plus delta x minus function of x over delta x is the approximation. Okay, that is very clear. We don't need to do the operation taking the limits of this given function, no? Is given fx plus delta x minus fx over delta x. We don't need to take the limit of that, okay, anymore. Just directly substitute x plus delta x to the function minus the function fx divided by delta x, and that's all. We can immediately get the numerical value. We can get an actual computation. That is the important thing about this, the lower formula. Okay, so therefore we have the famous general representation of approximation method for the first subtopic, forward difference approximation. Let us call this forward difference approximation method. We have the following details. X is necessary for us to be able to evaluate fx, and x plus delta x is necessary for us to be able to evaluate fx plus delta x. Okay, so there are two heights. There are two range of values. There are two values that we need to evaluate, fx and fx plus delta x, as you can recall from the previous page. Okay, so since we know the value of delta x, because it is a finite quantity. Finite quantity meaning it has certain amount, it's a certain value. It depends on you. It depends on your capability as an engineer, or it depends on your tools or computer's capability as available technology has given us the power to choose. Okay? So it depends. But it has a value. Now, you can see forward difference because from x, we forward to another value, which is x plus delta x. For example, x is, give a random number. For example, x is 10 and delta x is 1. So therefore, x is 10 here, as you can see here, this is 10, and x plus delta x is 11 because 10 plus 1 is 11. That is an example, okay? And therefore, if I ask you, find the value of fx at x is equal to 10. So you can easily substitute the value of 10 for the x variable and then evaluate the function, and you can get the amount, the quantity for fx. And that amount is this one. This one from this point to that point. So this height is actually our fx. And if I another thing, if I ask you, what is the value of fx plus delta x? So substitute instead the value of 11 rather than the value of 10 for the variable x, and then evaluate the function again, and you will find that the value is actually from this point, the height of this graph from this point to this point. What is this height? That is actually our fx plus delta x. Okay, so this is a graphical representation of forward difference approximation of first derivative. First derivative, it is clear that you know calculus, that you know geometry, you know trigonometry. This is what? First derivative is just a slope. It is a slope, so therefore you can calculate the slope graphically. You can calculate it numerically. Okay. Example number 1. The velocity of a rocket is given by the function. There is a given function, which is v, function of time, is equal to 2000 natural log of quantity 14 times 10 to the fourth divided by 14 times 10 to the fourth minus 2100 t minus 9.8 t. So that is the function. Wherein, what is the valid domain? The valid domain is t from 0 to 30, including both 0 and 30. Okay, that is the domain. Okay, where v is the variable given in meter per second and t is given in seconds. Therefore, t is representing time. The question now, therefore, letter A, use forward difference approximation of the first derivative of v, function of t, to calculate acceleration at t is equal to 16 seconds. Use a step size of delta t is equal to 2 seconds. So we have a finite value of delta t. In our previous slide, that is delta x, because x is a variable and now the given variable x is time. So delta t is equal to 2 seconds as given by this problem. Okay, so we can do that. Another question, letter B. Find the exact value of the acceleration of the rocket. So this is velocity of a rocket given by this functional representation. Okay, v is a velocity of rocket as given by the problem. And another question, letter C, calculate the absolute relative true error for part B. Okay, we can recall, what do we mean by absolute relative error? Absolute relative true error. True error, relative true error, absolute relative true error. And we can easily recall that from our chapter 1 introduction. There are several videos, and you can look back at our video that is particularly pertaining to errors. Okay, so let us proceed in solving this number 1 example solution. Okay, if we can take the first derivative of velocity, that is actually acceleration, as we learned from calculus. Okay, from calculus and from P6. No? So taking the derivative, first derivative of velocity function, we have an acceleration function. But this time, we disregard the limit operation and just what? Equate it as an estimate, as an approximation. So the acceleration function of time is approximately equal to velocity function of time I plus 1, okay, time I, that is x, that is equal to x, time I plus 1, that is equal to x plus delta x. Okay? Okay? Are we clear? That is another way of nomenclature pertaining to the same values. Okay? Take note, don't be misled, because our independent variable is time. We have what? Ti plus 1, that is equivalent to t plus delta t, okay, minus velocity function of ti. Okay, and divide by the finite value delta t. So since our time ti is equal to 16 as given by the problem, and delta t is equal to 2 seconds given also by the problem, so we can therefore find out that ti plus 1 or ti plus delta t is equal to 18. That is 16 plus 2 is equal to 18. And therefore, we can easily solve that the acceleration at t is equal to 16 is just equal to velocity at 18 minus velocity at 16 divided by 2. We can immediately calculate that value knowing our calculus. Okay, so and therefore we need to calculate velocity at time is equal to 18 seconds. And what is that? Use the same function, just substitute the value of 18. Okay, so substituting the value of 18, we can have the velocity at time 18 is equal to what? Use your calculator. Please use your calculator as a practice. So input in your calculator 2000, then press natural log, then press quantity, then press 14 times 10 raised to the exponent 4, then divide by quantity 14 times 10 raised to the exponent 4 minus 2100 times 18 close parenthesis, another close parenthesis, minus 9.8 times 18, and press equal sign, and you will get 453.02 meters per second. Okay, so please check your calculator. If your calculator is correct, it will give the same answer. And now, since we already know the velocity at 18, we can now next solve for the velocity at 16. Oh, the same equation, you will notice that you have only to change the value of 18 to 16. So use the same in your calculator, just backtrack and delete so that you can change the value of 18 to 16. There are only two here. So this 18 change to 16. This 18, another change to 16. So you can do it by your calculator. You can just back and move the cursor to the place with 18 and then delete. So okay, you can only delete 1, 8, and then replace by 6. Then move again to the other 18, then delete, then change 6, press 6, and then press enter. And you will get the result equal to 392.07 meter per second. And therefore, because we already know these two values, we can substitute our approximation. And that is velocity at 18 minus velocity at 16 divided by 2. So just do it. And 453.02 minus 392.07 divided by 2. And you will get what? 30.474 meter per second squared. Second squared because it is what? Acceleration. So that is the acceleration. This is the acceleration at 16. Take note. We are asked for the acceleration at 16, but we solve the velocity at 18. This is why our method is forward difference. Okay? Forward. 18 is a forward number from 16. Okay? Take note of that. And letter B, let us solve the letter B question. The exact value of acceleration at 16 can be calculated by differentiating, meaning using calculus. Using calculus, we can do it immediately, taking the derivative. And you know, it is very easy to take this derivative. And we can get the what? The acceleration function. Okay, and this is now our acceleration function. Okay, and after this, let's what? Let's do the necessary simplification. I don't need to do this. If our subject is calculus, I will do this calculus step by step. But our subject is not calculus. It is your responsibility to recall, to review calculus. Okay? So that we can limit so much waste of time. That is not actually waste of time in terms of learning, but waste of time in terms of lecturing, in terms of discussion regarding numerical method, because we have to limit our time into numerical methods rather than other subject. Okay, okay, take note of that. And therefore, our acceleration function would be simplified into this rational number, which is equal to what? Numerator negative 4040 minus 29.40 divided by denominator of negative 200 plus 3t. That is our acceleration function. And now we can just substitute 16 as the value of time. Okay, using that, substitute the value of 16 here, and then you can calculate that the acceleration at 16 is 29.674. Okay, if you can still recall, on letter A, our approximation is 30.474. Okay, our actual value is 29.674. So we can what? We can compute for the next number, absolute relative error. This is the question number letter C. Absolute number of true value minus approximate value divided by true value, and you will notice that our error is only very small error. This is acceptable because this is less than 3%. Our error is just what? 2.6967%. Less than 3%. What do you mean by 3%? For every 100 pesos, 3 pesos is 3% of 100 pesos. So, and we did not even get to 3 pesos. We only have 2 pesos and 70 centavos. Okay, so less than 3 pesos. So this is acceptable error. This is acceptable error. That is a very good result because our delta t, as you recall in this problem, is 2 seconds. Imagine 2 seconds. 2 seconds is very large. What is the speed of the fastest man on earth? If you add 2 seconds to that fastest man, a record for 100-meter dash, that guy will not what? Will not get any medal. The difference of competition of different runners, different sprint runners in Olympics is so great, is so small. And if we are talking of 2 seconds, that is a very large value if we are talking about a sprint runner. Okay, so the delta t here, the delta t, the acceptable error in domain is 2 seconds. That is a large value. And if we do the same example, okay, this is your assignment. Do the same example and use delta t is equal to 1 second. You will find out that the absolute relative true error is so little. It may not even get to 1%. May not even get to 1%. So prove that to me. Give your answer, solution as a comment in this video. So prove that to me. Okay. So, so that's all for our forward. That's all for our forward difference approximation. Okay. So the next video, we will talk about the other method, which is backward. So again, this is Dr. EYPEI, preaching engineering for nation building.